Greetings and welcome to the second lecture for ergodic theory. Today's lecture will be about compactness of the space Mx. We will begin with reviewing a few of the terms that we set last time. We're dealing with XD, which is a compact metric space. On XD, of course, we have a topology and therefore we have a Borel sigma algebra. The set Mx as a set is the set of all possible probability measures on the Borel sigma algebra. What we saw last time is that the Riesz representation theorem says that Mx embeds into Cx star, the dual space of Cx, where Cx was the space of continuous functions from x to r equipped with the norm, the supremum norm. This in fact implies that Mx is compact, but that uses a theorem, the Banach-Alaoglu theorem, which we never proved. And our goal today is to prove that Mx is compact. Now, in fact, one can skip today's lecture because, as we discussed last time, Mx is compact as an application of the Banach-Alaoglu theorem. There are a couple of reasons why I don't want to do that. The first, obviously, is that we have not proved the Banach-Alaoglu theorem, and it's not really good to use theorems that you haven't proved. Another reason is that I feel that the discussion of compactness of Mx will give us better understanding and make us more comfortable with the terms involved. And lastly, it will demystify the whole concept. There is something scary, perhaps, about using theorems that involve terms that were not properly discussed. Recall from last time that because XD is a compact metric space, we have that C of x, the space of continuous function on XD, is separable. So there are already two exercises that you might want to do on this first slide here. One exercise is to show indeed that Cx is separable. The other is to show that Mx is indeed compact and that follows from the Riesz representation theorem combined with the Banach-Alaoglu theorem. Anyway, we will fix for the remainder of this lecture a set Fj, a countable set Fj. J goes in ranges in the natural numbers, that is dense in Cx. In order to show that Mx is compact, we will start by fixing a sequence of measures, mu I in Mx, and proceed to prove that it has a convergent subsequence. It will sometimes be convenient to look at Cx star, the bounded linear functionals on Cx, and the Riesz representation theorem tells us that each mu I corresponds to one such representation, which we will denote as Ji. So Ji, recall from last time, is simply the integral given along the entire space given by the measure mu I. The key that we will use throughout this lecture is that because we are talking about probability measures, the integral of any function is at most its sup norm. This will be used many times throughout the lecture when we will say, once we fix the measure, therefore we fix this specific type of linear functional, the total integral on the function is at most its norm. Here's a quick reason, the proof. The value of the functional we're talking about, which is just the total integral based on this measure, is less than or equal to the integral of the absolute value of the function, that's just the triangle inequality, which in terms is less than or equal to the sup norm because the sup norm is an upper bound for the value of the function. And now you can take this function out because it's just a constant here, and you get the constant times the integral on the entire space, which is 1. That's the property of being one of the properties of being a probability measure. For each j in a sequence then, we have one function f sub j, and we know that the value of the functional of f sub j is bounded. So this gives us a bounded fixed sequence, j sub I of f sub j, which I now see as a sequence in I. We have fixed j. Well, such a bounded sequence then must have a convergent subsequence. Let's see what this gives us when we just look at j equals 1 our first function f1. We say then that the sequence ji of f1 is bounded and therefore has a convergent subsequence. Let's look at this convergent subsequence and let's just look at the functional for this convergent subsequence ji when I ranges on some index set a sub 1. So what is a sub 1? A sub 1 is an infinite subset of n. N was the original set of indices, and we just said we will take a a convergent subsequence. So as a recap, we obtain a1 inside n, which is an infinite subset, so that the set of measures mu I, where I ranges only in a1 and not in a, satisfy the property that this specific integral converges. And we'll construct these sets a1, a2, a3, and so on by induction. So suppose that an was already constructed. And what are the properties of an? Well, an was obtained from an minus 1 as a subset because it's subsequencing. It's still an infinite set. That's also a property of subsequencing. And we have chosen it so that this specific limit as I goes to infinity of the integral of fjd mu I converges if I ranges only on an. But then it follows that this integral also converges for 1, 2, 3, and so on up to n minus 1. And why? If you think as f sub j for j equals n minus 1, f sub n minus 1, well, by construction, the limit as I goes to infinity and I is restricted only to a minus 1, this limit converges, and an is a subset of a minus 1. Subsequence of a convergent sequence converges. So now we're going to apply the same logic to n plus 1. ji of n plus 1, this sequence of real numbers here, is bounded. Because it is bounded, it admits a convergent subsequence, and that convergent subsequence corresponds to indices which we call a n plus 1. What we get from the construction is that the limit as I goes to infinity of the integral of this function fj d mu I, the limit written down here at the bottom of the slide, converges now for all j starting at 1 and going all the way to n plus 1. We continue doing this and we get an infinite sequence of subsets of n, starting with n itself and getting a1, a2, a3 as above. It may look like we're done, but unfortunately we're not done, because of course it is possible that this sequence is the intersection of all these sequences, is finite or even empty, and that does not allow for subsequencing. You can just think about a1 being all the even numbers and a2 being all the numbers divisible by 3. Well, you already have only the even numbers, so if you keep divisible by 3 now, they're actually divisible by 6, and make it divisible by 5 after, and so on. Eventually you will lose every one of your numbers. Or if you just think about numbers bigger than 1, bigger than 2, bigger than 3, that's already enough in the intersection to lose absolutely everything. So what are we to do? What we are to do is to apply a diagonalization argument. We will produce a new sequence which we will call k of n. K of 1 will be simply the smallest number, the first number that appears in A1. K of 2 will be the second number that appears in A2. K of 3 will be the third number that appears in A3. Because these are subsequences, we see a few things. First of all, K of 2 is the second number appearing in A2. It's possible that it's the second number that appears in A1, but it is not possible that it's the first number that appears in A1. K of 3, being the third number in A3, appears in A2 because A3 is in A2 and appears in A1. But K of 3 has to be the third or further down the line number in A2, and similarly for A1. What this tells us is that K of 1, K of 2, K of 3, and so on are all distinct numbers. This is actually a sequence of natural numbers that does go to infinity. Note one more thing that will be useful to remember later. Because of this inclusion here, if we look at specific AM, of course Km itself is in AM. It's the mth number in AM by construction. But if we look at a specific AM and we look at Kn for n bigger than m, Kn will still be in AM. Let's think about m equals 1, for example. Well, K1 is in A1 by choice. K2 is in A2, but A2 itself is in A1. K3 is in A3, and A3 is a subset of A1. So we see that K1, K2, K3, they're all in A1. And this applies for all m. This will play a role. Why? Because when we look at this sequence Kn, and we look at it starting at some point m, we get a sequence which is a subsequence of AM itself. And because of that, we now see that for that specific m that we were talking about, let's look at what happened to Fm, and let's ask whether this sequence here converges. Well, convergence of sequence is a property of the tail, so we don't need to worry about what happened before m. Starting from the value m itself, Kn is contained in AM. So the tail of this sequence of K of n, the tail of this sequence is a subsequence of the tail of AM. And we know that this integral converges if we restrict ourselves only to values in AM. So now the tail is a subsequence of the tail of AM, and therefore, for j equals m, this converges. But m was arbitrary, so this sequence converges for all j. This is, of course, the key, that we got a subsequence that always converges. Getting back to the Riesz representation theorem then, excuse me, I got ahead of myself. Before we get back to the Riesz representation theorem, remember that in the very beginning, in the first slide that we discussed, we said Cx is a separable space simply because X is a compact metric space, and therefore we could fix ourselves a sequence Fj which is dense in Cx. And that is the sequence that we worked on throughout the entire lecture until now. Well, because it's dense in Fx, continuity tells us that this limit, which we saw on the previous side right here in the bottom, exists for every element of Fj. It in fact exists for every function f in Cx. And now this convergence is for all functions of Cx, and it's just a property of the way we subsequenced the measures that we were talking about. Now getting back for convenience to the Riesz representation theorem, we know that each one of these integrals here, when we consider f, the red function f in it, as a variable, is in fact a bounded linear functional on Cx. So this corresponds to an element of Cx star. We can call it j of Kn. Defined here, j of Kn of f is simply the value of the integral. And what equation 1, the equation here tells us that this limit converges. This is actually not an equation, there's no equal sign in it. But what this statement that this integral converges tells us that as a sequence of functional, jkn converges to some functional which we can call j infinity. The Riesz representation theorem tells us that j infinity corresponds to a unique probability metric, which we might as well call mu infinity. And what we have concluded here is what we wanted to conclude, that mu of Kn converges as n goes to infinity to mu infinity. And that is our subsequence excuse me, I obviously had to fix a little typo there on the slide. That is a subsequence showing that mx is compact. One remark that I wanted to make about this, of course, compactness or not compactness, this all depends on the topology that you choose. And we chose a topology on CX star that was called the weak star topology. Now, the weak star topology is a topology that was designed to make all the functions from CX star to R continuous. All the functions is impossible. I did not say that right. To make the functions from CXR star to R continuous when these functions are given by evaluation of functionals in CX star on functions in f of x. In other words, we test convergence in CX star by seeing what happens to function in fx when we apply the functions from CS star 4 to them. And I've written on the slide when we apply the integral, which was the case in our discussion here, but I really should say when we apply an arbitrary functional j, like so. Here's our j. Well, this corresponds exactly to the convergence in weak star topology that we have used today, meaning that the compactness that we established is indeed compactness in the correct topology. Okay, so that's it all today. If you're still listening to this, it means that you chose not to skip today's lesson, and that, of course, is something I'm very happy about. Our next lecture, which I'm hoping to post soon, will not be exactly about ergodic theory, but rather about convex sets, because we will need some convex geometry in order to understand the space Mx. This is simply because Mx itself is a convex space. Convex sets are naturally much easier to understand in finite dimensions, and that will be on this discussion next time. Until then, goodbye.